Hi, and thank you very much for this kind introduction, and welcome to my talk about an automated ROI-based analysis for 3D multi-voxel MOS sequences. And maybe this will help to make MOS a little bit, to see more MOS here at the OHBM conference in the future. Let's see. Before I want to introduce my method, I want to talk a little bit about the importance of tissue correction strategies for MOS and give you some examples what can be done. So especially when you take a look at certain metabolites, we have the problem that we deal with very low concentrations in the brain. So for example, for glutamate, we have concentrations about 5 to 50 millimolar and even 1 to 2 millimolar for GABA. So the next problem is that we have different metabolite concentrations in gray matter, white matter, and CSF, whereas we usually neglect the proportion of CSF in MOS data analysis. And especially for single voxel MOS, where we have very huge voxels, it's inevitably that we have different tissue types within this single voxel. Furthermore, we have to deal with partial volume effects, which has to be considered, definitely. So what can we do now, especially for single voxel approaches? Well, usually a segmentation into gray matter, white matter, and CSF is performed. And then you either take the proportion of CSF and subtract it for your analysis, but here you would neglect the different concentrations in gray matter and white matter, or you just take gray matter, the proportion of gray matter for your analysis, but hence here you would neglect the concentrations in white matter. In a more complex models, you can also use all the different tissue composition as covariates in your final model. When you take now a look at multi-voxel MOS data, we have one huge advantage. So we have many voxels across the brain, so we can take a look at many regions at once. And this will help us to see differences in regions where we maybe don't expect any changes in comparison to single voxel MOS. So for multi-voxel MOS, when you take a look at the single voxels in this grid, we have probably two approaches. Either we take bigger voxels, which have high SNR, so enough SNR in one single voxel, or we take smaller voxels and then perform a clustering. This is an approach where they took bigger voxels in the grid, and then for the analysis just chose single voxels out of the multi-voxel grid, and in the region they wanted to fit them in, and did the analysis in these single voxels, basically. This is very highly dependent on this MOS sequence you use. Some sequences allow, in the post-processing step, to move your voxels in the grid, and which is kind of an, let's say, interpolation step. Another approach is the clustering. So this is a sequence where they have very small voxels with low SNR, so they need to perform a clustering of many voxels and by spectral averaging to increase the SNR, and usually do this in manually drawn regions. There's one automated approach for this. This is the so-called MEDA software provided by Professor Maudsley. So they have small voxels, use some spatial averaging, and transform their MOS data into the MNI space and use some kind of use the AL atlas. So they need to cluster many of their voxels and perform the analysis within these regions. But however, this software package is basically just applicable for their own sequence, and not you cannot use it for any other sequences. So this led us to provide some post-processing step which should be available for many other MOS sequences, so in an ROI-based manner. What we have is we have some nice GABA editing MOS sequence with megalaser acquisition. So we have a field of view of about 160 millimeters in all dimensions, and a volume of interest of about 80 times 90 times 80 millimeters. So we get in the end a voxel size of about 1 cubic centimeter. As a second step, we needed some structural images. So we have some T1 rated images, MPRH, with a voxel size of about 1.15 millimeters, and use this for our analysis. So this is basically our work stream. We have like some parallel work stream. In the first step, we take our anatomical images and do an automated segmentation using FreeSurfer, which creates masks for our different regions, and then extract these masks. And for our spectral data, we use LC model for the analysis and then do some interpolation of the spectral data. And this is then highly dependent on the sequence you use, which interpolation you can do, or how this is applicable for your regions, or how you have to cluster single voxels in your sequence you use. What you do next is then basically an overlay of the masks and our spectral data. We use Mink and MATLAB for this, and then get some values within our regions of interest for all regions basically you want to have. So for the next step, we did some comparison to show, okay, that this works as well as manual labeling. So we chose like 4 regions, the left and right hippocampus and the left and right putamen, and did some comparison between automated and manual labeling. So we see here the data distribution for these regions for GABA to NA ratios and GLX to NA ratios, and did some interclass correlation coefficients. And basically we saw that we have the same data distribution with manual and automated labeling, which is pretty promising that at least it works as well as manual labeling. So what are now the benefits of this ROI-based approach? First of all, we have an automated labeling in the individual space, which is very suitable for longitudinal studies, especially for when you look at single subject levels. Furthermore, we can tremendously reduce the hands-on time compared to manual labeling approaches, and we lose any bias due to some manual labeler. Furthermore, this aims to be applicable for various types of MRS data, so it's just a tool you can use in your post-processing step, basically. And we have the investigation of just single tissue types depending on the regions you defined, so just gray matter or white matter or whatever you like. Of course, there are some limitations. You have to consider partial volume effects. So especially this is true for all basically multi-voxel data. So when you look at a certain voxel adjacent, the signal from adjacent voxels will influence the signal in the voxel you look at. You have to consider that, of course, for your analysis also in the region-based approach. And what is also very important is to choose adequate ROI sizes. So depending on your original voxel and the SNR in your voxel, we chose some voxels where we have at least 1 to 2 original, also size of 1 to 2 original voxels to get enough SNR in our region and to get reliable results. We are currently preparing a paper on this, and within this paper we also are very happy to share these codes and software tools. So if you're interested, just contact me or wait till the publication is out. So that brings me to an end. I want to thank my team, my supervisor, Professor Lanzenberger, and our collaborator, Professor Wolfgang Bogner, who provided this wonderful MRS sequence. And now if you have any questions, just feel free to ask me or contact me if you're interested in this analysis stream. Thank you very much.